Okay, as we're heading toward right triangles in Chapter 9 here, we've got to make sure that our um, manipulation of radicals from the last 2 years is honed and ready to apply to our geometry context. So, some problems, again, we've seen this year crop up here and there and everywhere, where you're asked to simplify a radical and it's a specific number. For example, square root of 40 or square root of 100. Now, you'll notice in front of the radical, we don't have anything written in front of these radicals. And that, believe it or not, that nothing tells you something. It tells you that those two numbers are positive numbers. And just like when we have, for example, the number 7 or the number 3.24, if we don't have something written in front, it means it's positive. If we want to talk about the opposite of 7, then we would write negative 7 or negative 3.24. So again, when I have this, root 40 or root 100, and I have nothing written in front of it, it means that it's positive. So let's go back and consider that root 40 again. Root 40 we know is a positive number because there's nothing in front of the radical sign. And we know that 6 squared is 36 and 7 squared is 49. So we know it's going to be somewhere between 6 and 7. And if you've got a square root that's some specific number, you want to kind of, before you simplify, you want to have kind of an idea of where you're heading toward. And what I'm looking to do when I simplify square roots is I'm looking to find factors of perfect squares under my radical sign. And I want to find the biggest perfect squares under the radical sign. What I'm looking to do is to take advantage of the fact of something like the square root of 6 squared is positive 6, or the square root of 11 squared is positive 11. I also need to keep track of my rule that the square root of a times b, where either a and b are both negative numbers or a and b are both positive numbers, because I have to have a positive number under the square root. We're going to deal with real numbers in this course. That's going to be root a times root b. So I want to use this factor, this thought, and this thought in simplifying root 40. So root 40, if I look at perfect squares, the biggest perfect square that's a factor of root 40 would be 2. Would be 4 is a perfect square, and then take that, it's 2 squared. So it's 2 squared times 10. I then can go ahead and break up that 2 squared into root 2 squared times root 10, using this rule over here that we just talked about. The square root of a times b is the square root of a times the square root of b. The square root of 2 squared is 2. And what about root 10? Root 10, there are no perfect squares of 10, or if 10 has no factors that are perfect squares. So I can't simplify root 10 any further. Indeed, root 10 is in what's called simplified radical form. So I've come up with what I think is an answer. Well, root 10 is about somewhere between 3 and 4, because 3 squared is 9 and 4 squared is 16. 2 times 3 and a bit is going to be somewhere between 6 and 8. And remember, we looked back up. Here at root 40, and we said it had to be somewhere between 6 and 7. So somewhere between 6 and something looks reasonable. So 2 root 10 looks good. So how about that root 100? Root 100 is one number. It's a positive number because there's nothing, no symbol, no negative sign in front of the radical. So root 100 is root 10 squared, which is simply 10. And we would say that 10 is the principal or positive square root of 100. Now let's suppose I give you a different situation. I haven't asked you to simply simplify a square root. I've asked you the following situation. I've given you an equation. I've said some number squared equals 100. And is there more than one number that when I square it, I get positive 100? And the answer is indeed true, plus or minus 10. And hopefully by inspection, I will simply answer that question and say plus or minus 10 and not do a heck of a lot of work in writing. If I were to do it in writing, whenever I take a square root, if I've got an equation and I'm going to take the square root of each side, on one of the two square roots that I take, I have to put a plus or minus. And it doesn't matter which of the two I pick to take the plus or minus. The square root of x squared in this case will be x, and I've taken care of the plus or minus business by putting a plus or minus in front of the 100. So indeed, algebraically solving it, I get plus or minus 10. Okay, now the other situation that's cropped up and will crop up for us is suppose you're giving something like 3 squared, square root of 3 squared plus 4 squared. Again, I know that that's a positive number because there is no negative sign in front of the square root, so that's a positive number. And the error that was made over and over again in pre-alg and in Algebra 1 by students is to get excited and say, oh, I've got the square root of squares, so I'm going to simply go ahead and say that's the square root of 3 squared is 3, and the square root of 4 squared is 4, and I'm going to get 7, and I'm done. And the problem with that, what makes that different, and why this is incorrect and you cannot do, is you are under the square root. I don't have a product. I don't have an a times b. I have an a plus b. The big picture is addition here. The big picture is addition or subtraction. It doesn't matter that you have squares. You have to write in terms of simplifying what's under here first, or you need to write it in factored form first before you can take the square root. Indeed, our rule was the square root of a times b equals the square root of a times the square root of b. But up here, note, we don't have times, we have plus. So, we've got our square root of 3 squared plus 4 squared. Any common factors to try and get this into factored form between 3 and 4? And there are none. So I've just got to go ahead and go, well, 3 squared is 9, 4 squared is 16, 9 and 16 is 25, and the square root of 25 is 5. And that's how I'm going to deal with that problem. Now, suppose I have something, again, like 30 squared, or let's do 300 squared plus 400 squared. The first thing you might notice is I do have that 3 and 4 again, and we're going to be looking for what are called Pythagorean triples. Triples such that the smallest number squared plus the middle number squared equals the largest number squared. So indeed, I see this 3 and 4, 3 squared plus 4 squared. So I'm going to guess that it might have something to do with a Pythagorean triple. In this case, I do have the big picture being something plus something under the square root. So my big picture here is addition. And if I want to simplify this using my rule that if I have factored form under the radical, I might be able to do something interesting. Indeed, that's where we want to head. So I want to look for the greatest common factor between the 300 and the 400, and that's going to be my 100. So I can go ahead and pull out a 100 and write this then as 3 squared plus 4 squared. And now, indeed, I'm in factored form. I have 100 times 3 squared plus 4 squared, which means then that I can rewrite this as a square root of 10 squared times the square root of 3 squared plus 4 squared. Square root of 10 squared is 10. Square root of 3 squared plus 4 squared we just did was 5, and I get an answer of 50. Okay, last one again. Suppose we have the following, and we say, oh, we've got a 3 squared and 5 squared. Oh, then that answer must be 3, 4, 5, so I've got 4 over here. The problem with that is that 5 in that 3, 4, 5 triple was the largest number. And if I go ahead, 3 and 5 have no common factors, so since I am adding under the radical, I don't have factored form, I actually have to go ahead and get 9 plus 25. I know that 3 squared plus 5 squared is 9 plus 25. I know I get root 34. Root 34 has no factors that are perfect squares, 17 times 2, so I am in simplest radical form, root 34. And note, root 34 does not equal 4. And the last thought, again, looking ahead, we're going to deal with numbers here primarily in this chapter, because we're going to look at right triangles and the Pythagorean theorem, so we'll be working with a lot of numbers, which is great. But heading on to algebra, you're going to be asked to simplify something like the square root of x squared. And you might say, well, we just did the square root of 5 squared is 5, so the square root of x squared, that's going to be x. But what happens if x equals negative 2? Well, if x equals negative 2, then the square root of negative 2 squared equals the square root of 4, which equals, note, we don't have any negative sign in front of that square root, so it has to equal 2. But are 2 and negative 2 the same number? And the answer is no. So if x were a negative number, which is permissible here because I'm going to square x, which is going to make it positive, but then I don't get x out. So what do we do in this situation? Well, what we can do is we know that we want to make, if we've got the square root of x squared, we know our answer has to be positive. And we know if x is positive, we're in great shape. The square root of 2 squared is the square root of 4, which is 2, all good to go. But if x were negative, we had to take its opposite. So one way to deal with this is simply say the square root of x squared is the absolute value of x. And we remember that the absolute value of x represents the distance from x to the origin, and distance is always positive. So if x were positive or negative 2, if x were positive or negative 2, the distance to the origin is going to be 2 in each case. So, again, from Algebra 1, just a little review, the square root of x squared, one way to do that, keep track of it, is x.